This is Zach Nicander, and welcome to my presentation on force during a hockey slapshot for Physics 107 with Professor Dan McIsaac. For many of us, sports are an outlet. They give us a chance to test our limits and achieve feats that we may have never envisioned. To me, there is no better representation of this than hockey. During competition, players are subconsciously using mathematics to win the game. This includes geometry, but also more importantly, physics, whether that means directing a pass or positioning our body to apply the maximum force during a slapshot. The laws of physics are always relevant. In this presentation, I will calculate the force applied during my very own slapshot. Hockey sticks are built to be flexible. This allows the player to use the stick as a type of spring mechanism. It's hard to see in real time because the game is just so fast, but during each shot, players' sticks are actually flexing and returning to their original state upon the follow-through. Stick manufacturers label retail sticks with a number anywhere from 20 to 110 in most cases. This value represents the amount of force in pounds needed to flex the stick 1 inch. Most adults fall between 60 and 100 flex. Typically, the flex is approximately half of your body weight. Pro stock sticks vary much more than retail sticks. For example, 6'9", 250-pound Zdeno Chara has been rumored to use a stick close to the 140 flex range, which is unheard of for the average human. He, like many other professional players, possess an incredible amount of strength and leverage in order to use a stick of such size. To put that into perspective, I use a 75 flex stick. This means that at the time the stick was new, it required 75 pounds to flex the stick 1 inch. This has since changed due to me cutting about 2 inches off the shaft and the stick breaking down over time from consistent use. To simulate the flex on the stick during a shot, I set up an experiment to test how much force is actually required to flex my stick. To do this, I set up 2 tables and placed my stick in the middle so that only about 1 inch of the stick was touching each of the tables. I then placed a string spanning from one table to another exactly 1 inch below the stick. I then suspended weight from the shaft of the stick in the form of Olympic weight plates with a heavy rope. We continued to add weight until the stick bent to our goal of 1 inch. I learned that my stick actually only required 71.5 pounds of force to flex 1 inch. To reiterate, the reason that it required less than 75 pounds was because of the gradual breakdown of the stick over time. Hockey players utilize the flexibility of the stick in a few different types of shots. Here I have examples of 3 shots: slapshot, snapshot, and wrist shot. Each shot is limited in the amount of force the human body is able to apply to the stick. As shown in my case, the snapshot produces the least flex, and the slapshot produces the most. Therefore, the slapshot allows us to best show this phenomenon. To perform this experiment, I will be using a shooting pad to simulate an ice surface. The pad is sprayed in Pledge furniture spray to increase lubrication. The backdrop is labeled with a ruler, and there are tape marks every 6 inches. The pad is also marked at 6-inch intervals. The puck will be fired into a net with an added backstop for safety. The camera I am using is from my Samsung Galaxy smartphone and is capable of producing slow-motion videos at 1080p for 240 frames per second, as well as super slow-motion videos at 720p for 960 frames per second. On the screen is a super slow-motion video of myself taking a slap shot. As we can see, the stick first contacts the ground, then contacts the puck and propels it forward upon the follow-through. A few important things to note about the experiment are the following. Each mark is 6 inches apart. The distance from where the puck starts until it reaches the end of the board is 30 inches. The amount of frames from the initial contact until the end of the board is 36 frames. And the total time it takes for the motion to complete is 0.0375 seconds. The video plays at a speed of 960 frames per second. That means each frame represents 0.00104166 seconds, and that also means that there is a total of 0.0375 seconds that will have elapsed from the contact of the puck until it reaches the end of the pad. Using these facts and conversions discussed in the previous slides, I was able to put together 3 graphs: position versus time, velocity versus time, and acceleration versus time. According to the acceleration versus time graph, the peak acceleration during the shot was 972.8 meters per second squared, which is found at the first timestamp on the graph of 0.0125 seconds. To calculate the force on the puck, I will be using the equation F net equals m times a. F net represents force. M represents the mass of the puck, and A represents the peak acceleration of the puck during the shot. The mass of a hockey puck is typically about 0.170 kilograms. The peak acceleration found in the graph is 972.8 meters per second squared. When these numbers are plugged into the F naught equals ma equation, the resulting value is 165.376 newtons. This means that at peak acceleration, there was a total of 165.376 newtons of force being applied to the puck.